So for our final topic today, we want to talk about the case k equals 4, namely what numbers are sums of 4 squares. So this is a very famous result of Lagrange that we're going to prove. And again, I want to reduce to the case of primes. It's going to be the same outline as for some things that are sums of 2 squares. We reduce to primes, the primes that we hope work, which in this case will be all of them, not just half of them. The primes that do work, we first show that there's some multiple of them that's a sum of 4 squares, and then we try a method of infinite descent, and then we tie all the primes together with multiplicativity. Right, so we basically need an algebraic identity yet again. So the lemma, which it's kind of a long, nasty-ish formula, right? So I've just written it in the board. The point is the formula exists. We'll have to refer to it later, but the exact shape of the formula is not really what's critical here. It's just the fact that some algebraic identity exists. And I've written it here. If you really feel like checking it, of course you can, but probably you don't want to. You just write it all out and it happens to be true. Doesn't say anything about where it comes from, but it's just a fact that in algebra that exists. So if m and n are sums of 4 squares, then so is their product, right? So the property of being a sum of 4 squares is preserved under multiplication, right? So specifically say that m is the sum of these 4 squares, a, b, c, d, n is the sum of these 4 squares, e, f, g, h, then m times n is the sum of 4 squares, square plus square plus square plus square, because it's the sum of these 4 squares. AE plus BF plus CG plus DH, AF minus BE plus CH minus DG, AG minus BH minus CE plus DF, and AH plus BG minus CF minus DG. So each one of the things that's squared in this formula is like a sum of 4 terms of products of 2 of the different numbers with plus and minus signs, all right? So, maybe if you expected such an identity to be out there, you could imagine writing some computer code and like searching for such identities. But anyway, it's a highly non-obvious algebraic identity. It's there, and that implies that m and n are sums of 2 squares, implies that their product is, right? So just as with the k equals 2 case, this reduces us to studying the Diophantine equation, p equals square plus square plus square plus square, where p is a prime. All right, and that's what we'll start in the next video.